Okay, so in section 2.7, if you turn to page 137 in your textbook and read the top of it, you'll find these key concepts that you should copy into your notes. The fundamental theorem of algebra. The theorem states, if f of x is a polynomial of degree n, where n is greater than 0, then the equation f of x equals 0 has at least one solution in the set of complex numbers. The corollary is, if f of x is a polynomial of degree n, where n is greater than 0, then the equation f of x equals 0 has exactly n solutions, provided each solution repeated twice is counted as 2 solutions, each solution repeated 3 times is counted as 3 solutions, and so on. So we've talked about this as we've gone through the rest of the chapter and started to find our zeros and our solutions to various polynomials. If you take a look at the degree, so in the first example, we have x cubed plus 5x squared plus 4x plus 20 equals 0. So it's degree 3, which means it would have 3 solutions, or 3 zeros. Remember that zeros, roots, and solutions all refer to the same thing. They're referring to those x-intercepts, the places where the graph will cross the x-axis and the output is 0, y value of 0. So for f of x equals x to the 4th minus 8x cubed plus 18x squared minus 27, the degree is 4, so there would be 4 zeros for that polynomial. So number 2, right below this, is to find all of the zeros of f of x equals x to the 5th minus 4x to the 4th plus 4x cubed plus 10x squared minus 13x minus 14. So pause the video and practice what we've been doing over the past few days. Actually find all of the zeros of that function. So start by listing the factors of the constant, the p-value, the factors of the leading coefficient, the q-value, then list out all of the possible rational zeros. You can graph it to find good ideas of starting points to start your synthetic division. And please realize you're looking for 5 solutions. So you're going to need to do 3 rounds of synthetic division to get it down to a quadratic, unless we get lucky and some terms drop out along the way. But go ahead, pause the video here, try example 2. When you've solved it and you have all 5 solutions, come back and press play on the video to see how you did. Okay, so how did you do with example 2? Were you able to find all 5 zeros? Here's the work for this problem. So the constant was negative 14, which means p, the factors of the constant, would be plus or minus 1, plus or minus 2, plus or minus 7, or plus or minus 14. The leading coefficient is 1, so q, the factors of the leading coefficient, are plus or minus 1. Because q is just plus or minus 1, it means the possible zeros are just the p-values, because p divided by q would stay the same. So I graphed the function in Desmos in order to begin finding good ideas of where to start. So in Desmos I typed in this function, and when you type in that long polynomial, you'll see something that looks like this for the graph. And I can readily identify that I had an x-intercept at -1 and +2. But this example also brings in something we'll talk about even more in the next lesson, and that is double root. So a double root is when we have a rebound point. The graph comes up, hits the x-axis, and rebounds in the same direction. It doesn't actually cross through the x-axis. The y-values don't change signs. So it's kind of like it hits a brick wall and gets shoved back in the same way. And what that means is -1 is going to actually work twice in our synthetic division. 2 was another x-intercept or root. It's a single root though, because we see it travel straight through the x-axis. Y-values change from negative to positive. So 2 should only work once. So I brought down my coefficients from my polynomial, and I decided to start with -1. Remember, in synthetic, you bring down the leading coefficient, nothing happens to it. Then you multiply, put it under the next column, add these two together, multiply, put it here, add them together, multiply, put it here, add them, multiply, put it here, add them together, multiply, put it here, add them together. Now, when I start looking at this, so I see, yep, it is a 0 as the graph was showing us. So there's no remainder. This is the constant, the linear term, the quadratic term, the cubic term, the quartic term. So I don't have strategies to solve a fourth degree polynomial. I've got to keep dividing and get it down to a lower degree polynomial. So I build my next round of synthetic right off of the last. I don't need this column anymore, so the synthetic gets shorter. And I'm going to try 2 this time. Again, bring down your leading coefficient, nothing happens to it. Multiply, put it under here, add, multiply, add, multiply, add, multiply, add. Remainder of 0 tells me, yep, as the graph showed, that is definitely a 0. Here's my constant, linear, quadratic, and cubic terms. Again, I don't have strategies to solve cubic equations. I have to keep dividing to get it down to a quadratic. I can solve any quadratic. So, because the graph showed us this double root, this interesting point where it hits the x-axis but doesn't actually travel through it, it just rebounds back, that means -1 should work again. So I'm going to try -1 again. I build my synthetic right off the last one. Again, you don't need this column, so it gets shorter. Bring your leading coefficient down. Multiply, add these together, multiply, add these together, multiply, add these together. You see, yep, it worked. It is a 0. There's not any remainder. Here's my constant, my linear, and my quadratic. So now I know the full factorization. This is what I got for my last round of synthetic. Then -1 means x plus 1 is your factor, and there was another one up there. And then 2 means x minus 2 is your factor. So there's your complete factorization. Zero product property allows me to set each of these factors equal to 0 and solve. Well, I know the x plus 1's give me the -1's. The x minus 2 gives me 2. I just have to solve this, which unfortunately isn't factorable. I have to go to quadratic formula. So you start with the opposite of b, so +4 plus or minus square root. The b value squared minus 4 times a, which is 1, times c, which is 7, all over 2 times that a value of 1. So 4 comes down, plus or minus comes down, bring down your square root. -4 squared is 16, 4 times 1 times 7 is 28. In the bottom, 2 times 1 is 2, so 4 plus or minus the square root of -12, all divided by 2. Well, when you have a square root of a negative, you got to break it down. So we break this down into the square root of -1 times the square root of 4 times the square root of 3. Remember that the square root of -1 is I, the square root of 4 is 2, and 3 doesn't square root evenly. And so then that's how we got this. 4 plus or minus 2i square root of 3 all over 2. Then divide each of your terms by the 2. So 4 divided by 2 is 2. 2i squared root of 3 divided by 2 is I squared root of 3. So there are my final 2 zeros. It was a 5th degree polynomial. Here are the 5 zeros. -1 was a double root, so it came up twice. 2 plus I squared root of 3, and 2i minus square root of 3. So 2 complex or imaginary solutions, and 1, 2, 3 real. Okay, so here is another example of what we've been doing. So again, pause the video, go through the whole process, see if you can find all 5 of your zeros for this polynomial, then come back and check to see how you did. Okay, so how did example 3 go? First thing I gotta ask, did you fill your gaps? So there wasn't an x to the 4th power, so you had to fill it in with the plus 0x to the 4th. There also wasn't a linear term, so we had to add in plus 0x there as well. So that your coefficients for synthetic were 1, 0, -4, 1, 0, -4. The constant was -4, so p, the factors of the constant were plus or minus 1, plus or minus 2, plus or minus 4. leading coefficient was 1, so the factors of q were plus or minus 1. Therefore, the possible zeros were just the p-values. I graphed the function in Desmos, so I typed x to the fifth minus 4x cubed plus x squared minus 4 into Desmos. I got this graph, and I could see 3 single roots. I know they're single roots because they actually just travel straight through the x-axis and change value from positive to negative or negative to positive. Which tells me also that I'm thinking there's going to be 2 imaginary solutions since I only see 3 x-intercepts and none of them are double roots or triple roots or anything. So I decided to start with -1. So I put -1 down with my correct coefficients with the 2 gaps filled. I bring the leading coefficient straight down, nothing happens to it. I multiply, I put it under this column. I add straight down, I multiply. 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 I add straight down and see, yep, the graph wasn't lying. It really is a 0. There's no remainder. But this is the constant, linear, quadratic, cubic, quartic, so I haven't gone far enough. I don't have any way to solve a quartic polynomial. So I do another round of synthetic. I build right off of that one. I don't need this final column, so it gets a little shorter. This time I'm going to go with the positive 2 I see on the graph. I bring down my leading coefficient. I multiply, add, multiply, add, multiply, add, multiply, add. And so now I have no remainder because it is a 0. Constant, linear, quadratic, cubic. Again, I can't solve a cubic polynomial. I need to divide one more time to get it down to a quadratic. So I'm going to use my third x-intercept I see on the graph, which is -2. Bring the leading coefficient straight down, multiply, add, multiply, add, multiply, add. No remainder, so it definitely is a 0. Constant, linear, quadratic. And I now have my complete factorization. So this one gives me x plus 1, this one gives me x minus 2, this one gives me x plus 2, and this gives me x squared minus x plus 1. So these 3 with zero product property, quick and easy since they're linear. This one can't be factored, so I have to do quadratic formula. So the opposite of b would be positive 1 plus or minus square root, the b value squared minus 4 times that a value times the c value, all divided by 2 times the a value. So you have 1 plus or minus the square root of 1, take away 4, all divided by 2. So you have 1 plus or minus the square root of -3, all divided by 2. Because there's a negative under here, remember you got to break that down and think of that as the square root of -1 times the square root of 3. Square root of -1 is I, so you get I squared root of 3. So we have 1 plus or minus I squared root of 3, all divided by 2. And now we can list our 5 zeros because it was a degree 5 polynomial. 5 zeros, 5 solutions, -2, -1, positive 2, 1 plus I squared root of 3 divided by 2, and 1 minus I squared root of 3 divided by 2. Okay, so next we have 2 more key concepts. The first one is the complex conjugates theorem. If f is a polynomial function with real coefficients and a plus bi is an imaginary 0 of f, then a minus bi is also a 0 of f. This comes from the idea that imaginary numbers are the result of trying to square root a negative, and anytime we square root, we're going to have a positive and negative solution. So it's impossible to only have one imaginary solution. They always come in complex conjugate pairs. So that's what this complex conjugates theorem is reminding you. That if you have a plus bi, you have to have a minus bi, because the bi would have come from square rooting something, well, a negative number, and you always have plus or minus that. The irrational conjugates theorem is doing the same thing, only with square roots, with irrational values. So if you have a plus the square root of b, you'd have to have a minus the square root of b, because anytime you square root, you need plus or minus. So this is coming up now because we've been working on finding the zeros when given a polynomial. Now we need to work the other direction. So if we start with the zeros, can we work backward and find the polynomial. So number 4 says to write a polynomial f of least degree that has rational coefficients with 3, -2, and 4 as its zeros. So they're telling us that x equals 3, x equals -2, and x equals 4 are the zeros of the function, meaning if I get these each equal to 0, I'll start to see my factors. So for the first one I subtracted 3 from both sides, on the second one I'm adding 2 to both sides, and on the third one I'll subtract 4 from both sides. So that now I can see my factors that I must have set equal to 0 to solve and find those zeros. So then I can write my function. So f of x is going to equal x minus 3 times x plus 2 times x minus 4. The statement about least degree just tells us that none of these are double or triple roots or anything like that. They're all just single roots. So we know that this function would have to be a degree 3 polynomial. So there it is in factored form. We need to multiply it out and get it into standard form. So f of x will equal, I'm going to start by foiling my first two binomials, and I'll get x squared plus 2x minus 3x minus 6 times x minus 4. Or if I simplify that a bit, I'm going to have x squared minus x minus 6 times x minus 4. And so then if I use the double distributive property and distribute the x to everything, I'll get x cubed minus x squared minus 6x. And then I'll distribute the 4 to all three terms, and I'll have minus 4x squared plus 4x plus 24. So if I combine like terms, I'll have my polynomial in standard form. X cubed minus 5x squared minus 2x plus 24. That must have been the polynomial we started with in order to find our three zeros, x equals 3, x equals -2, and x equals 4. Here's our next example. Write a polynomial function of f of least degree that has rational coefficients, a leading coefficient of 1, meaning the a value is 1. We didn't address it in the previous example. To be formal, we should have put an a out front because we didn't know what the leading coefficient was. Here they're just simplifying it and telling us it's just a 1. And they're telling us that one zero is 3, another 0 is 2 plus the square root of 5. Well, by the irrational conjugates theorem, I know that if I have 2 plus the square root of 5, I must also have 2 minus the square root of 5 as a 0. So my zeros, 3, 2 plus the square root of 5, and 2 minus the square root of 5. So x equals 3, x equals plus 2 square root of 5, and x equals 2 minus the square root of 5. So if I work backward and get these equal to 0, I'll find my factors. So for the first one, subtract 3 to move it over. The second one, first I'll subtract the 2, then I'll subtract the square root of 5. The last one, I'll subtract the 2, then I'll add the square root of 5. And so there are the three factors. And so I'll start to build my polynomial. I called the last one f of x, but this one is also supposed to be called f of x. Okay, so f of x is going to be the product of those three factors. So x minus 3 times x minus 2 minus the square root of 5 times x minus 2 plus the square root of 5. Now you can multiply in any order you want, but in this case you're going to find it easiest if you multiply out these two first to get rid of all of those crazy square roots. So I'm going to use the box method because you always have the option, you can use, distributive property or the box method. I think with the square roots, it might be nice to visually see it in the box. Okay, so I've got x minus 2 minus square root of 5, x minus 2 plus square root of 5. So x times x is x squared. X times negative 2 is negative 2x. X times the square root of 5 is x square root of 5. Negative 2 times x is negative 2x. Negative 2 times negative 2 is positive 4. Negative 2 times the square root of 5 is negative 2 root 5. I can't actually multiply the 2 and the 5 because the negative 2 is not under a square root and the 5 is. X times negative square root of 5 would just be negative x square root of 5. Negative square root of 5 times negative 2 would be positive 2 times square root of 5. Negative square root of 5 times positive square root of 5 would be negative square root of 25, which equals negative 5. Okay, so now if I take a look at combining like terms, I see x squared of 5 and negative x squared of 5, so those are going to cancel out. I see positive 2 square root of 5 and negative 2 square root of 5, so those are going to cancel out. And so I'm going to be left with all whole values, no more square roots. So f of x equals x minus 3 times x squared. I can combine these and get negative 4x. Then I've got two constants, so I've got 4 and negative 5. So 4 plus negative 5 gives me negative 1. So now I'm going to multiply these. So this time I'll use the distributive property. So x times x squared is x cubed, x times negative 4x is negative 4x squared, x times negative 1 is negative x, negative 3 times x squared is negative 3x squared, negative 3 times negative 4x is positive 12x, negative 3 times negative 1 is 3. So we combine like terms, x cubed minus 7x squared plus 11x plus 3. And we find our polynomial that we must have started with in order to find the three zeros, 3, 2 plus square root of 5, and 2 minus the square root of 5. So it's important to note that they're not going to list both of the irrational zeros, or if we had imaginary, they wouldn't list both of the imaginary solutions because they don't have to. You know, as a mathematician, that if you have a square root, you must have included plus or minus. So if you have the positive case, you also have to include the negative case. So Descartes' rule of signs helps us to narrow down the possibilities. Sometimes when you list out P and Q and divide P by Q, you get a pretty large list of possible zeros, and you need good strategies to help you to narrow it down to ones that are actually good possibilities and would actually work. So Descartes' rule of signs says if you have this polynomial with real coefficients, the number of positive real zeros is equal to the number of changes in sign of the coefficients of f of x, or less than this by an even number, because the only way we could make them up and achieve the correct degree would be in the imaginary column. And remember that imaginary solutions always come in pairs. The number of negative real zeros then, or negative x-intercepts, would equal the number of changes in sign when we find f of negative x. And if it's not that number, it could only be less than that by an even number, because again we'd be making them up in that imaginary column. So for this function, f of x equals x to the 6th minus 2x to the 5th plus 3x to the 4th minus 10x cubed minus 6x squared minus 8x minus 8. First of all, let's find those possible zeros. Negative 8's factors are plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. The leading coefficient is 1, so q is plus or minus 1, meaning that the p-values are your possible zeros. So there are 8 possible real zeros. Let's see if Descartes' rule of signs can help us narrow down how many positive and negative there are. So in this original function, it starts positive, it goes to negative, it goes back to positive, it goes back to negative, and it stays negative the rest of the time. So there's only 3 changes in sign in the original function, meaning there are a maximum of 3 positive x-intercepts or 3 positive real zeros. If it's not 3, the only other option would be 1, because you'd have to make them up in the imaginary column, and imaginary come in pairs. So this column will always have even numbers in it, never an odd number ever, because it's impossible to only have one imaginary solution. They always come in 2s, from the plus or minus. Okay, so we now know that for positive roots, we've got 2 possibilities. We could have 3 of them, or we could have 1 of them. I can't go down by 2 anymore, I'd be in the negatives. So there's only 2 possibilities. We could have a maximum of 3, or we could have only 1. For the negative, I have to find f of negative x. So I replace all of my x's with negative x. And then I simplify. So negative x to the 6th power will come out positive, because if you multiply 6 negatives, they'll cancel out. It'll be positive. However, for the next term, negative x to the 5th power would be negative, times the negative 2 would turn it into positive 2x to the 5th. For the next term, negative x to the 4th would come out positive, because 4 negatives would cancel and give you a positive. Times the positive 3 gives us 3x to the 4th. Negative x to the 3rd power would come out negative, times the negative 10 gives us positive 10x cubed. Negative x squared would be positive, times the negative 6 gives us negative 6x squared. Negative 8 times negative x is positive 8x. And the constant is unaffected because it's not multiplied by an x. So what you should notice when you do this is the even powers will stay the same. So they'll keep the same sign. It's the odd powers that'll flip. So evens stay the same, odds flip, and that's because if you multiply negatives an odd number of times, it comes out negative. If you multiply negatives an even number of times, the negatives cancel, giving you a positive. So now let's count sign changes. So it starts positive, stays positive all the way to here. So there's our first change in sign. Goes back to positive and then back to negative. So there are also a maximum of 3 negative x-intercepts, or 3 negative zeros. Again, if it's not 3, the only other option would be 1, because I'd have to go down by 2 to pick them up in this imaginary column. So, reminder that the fundamental theorem of algebra tells us that the degree should match the number of solutions. So every row in my column should add, or every row in my table should add up to 6, because this is a degree 6 polynomial, and so there would be 6 solutions. Well, 3 plus 3 is already 6, which would leave 0 imaginary. If we only had 1 positive and 1 negative, we would need 4 imaginary, so that 1 plus 1 is 2, plus 4 is 6. And then I have to consider all of my other possibilities. I could stay with my maximum of 3 positive, but go down to 1 negative. 3 and 1 would add to 4, leaving me with 2 imaginary. Or I could go down to 1 positive and stay with my maximum 3 negative. 1 plus 3 is 4, so I would need 2 imaginary to get to 6. I don't need this final row in the table. Please know we just give you a generic table to help you stay organized. The number of rows does not at all imply how many possibilities there are. We have all the possibilities because we did maximum, maximum, minimum, minimum, max here with the minimum here, the minimum here with the maximum here. There aren't any other possibilities to try. I can't go down by 2 anymore. I'd have -1. Same thing here. So those are all of the possibilities. If we graph the function, we can see which one is actually correct. But so this would allow us to narrow it down and say, it's impossible for all 4 positives or all 4 negatives to work. So let's graph it quickly and see which of these 4 cases it actually is. Okay, so if you graph this function, here's a little snippet of the graph. We see 2 x-intercepts. One is to the left of the y-axis, which means it's in the negative x value, so there's 1, -0. The other is to the right of the y-axis, meaning in the positive x value, so we have 1 positive x-intercept. We only see 2 x-intercepts, so that means we must have 4 imaginary. We've got 1 positive, 1 negative, so it means that this row of the table is correct. And so if we're solving this to find the actual zeros with synthetic division, we now know that once we find our 1 positive 0 that works, we should move on to the negatives because there's only 1 positive and 1 negative, and then the rest are imaginary. Okay, so here's another example of Descartes' rule of signs. Determine the possible numbers of positive real zeros, negative real zeros, and imaginary zeros for f of x equals 2x to the 6, take away 3x squared minus x plus 6. So it's degree 6, meaning I should have 6 solutions, so every row of this table needs to add up to 6. I'm going to start by counting sign changes in the original. That's going to tell me how many possible positive zeros there are. So it starts positive, goes negative. There's 1 change in sign. Stays negative until right here. So there are 2 positive. There's a maximum of 2 positive real zeros. If it's not 2, my only other option is to make them up in the imaginary column, which remember is always even because we get imaginary solutions by square rooting a negative. So you'd have plus or minus 2, and they come in pairs always. So if it's not 2 positive, the only other option would be 0 positive. Because 2 minus 2 is 0. I cannot go down by 2 anymore. I'd be in the negatives. So I either have 2 positive real x-intercepts or none at all. Now I've got to find f of negative x. Okay, so f of negative x. I replace x with negative x and I see what happens. Remember, anytime you substitute, always put it inside of parentheses. If I simplify this, well, negative x to the 6th power is going to come out positive, because if you multiply a negative value 6 times, the negatives cancel. So positive x to the 6th times 2, positive 2, is 2x to the 6th. Negative x squared would come out positive, because a negative times a negative is positive, times the negative 3 gives you negative 3x squared. Negative times a negative is a positive, so that switches to plus, and the constant is unaffected. So again, you see that the even terms stay the same, the odd terms switch signs. Constant stays the same always. So now if we count, it starts positive, goes negative, comes back to positive, and stays that way the rest of the time. So there are a maximum of 2 negative x-intercepts. If it's not 2, your only other option is 0, because you'd have to make them up in the imaginary column. So if I take a look, I've got maximum of 2 positive, maximum of 2 negative, which means there has to be at least 2 imaginary solutions, because I need 6 solutions. This is a degree 6 polynomial. So that tells us this polynomial does not have all positive or negative x-intercepts. It's got at least 2 imaginary. If we do the minimum number of positive and negative, so none of each of those, then all 6 would have to be imaginary, meaning that the entire function is above the x-axis or below the x-axis. Or I could, flip up my possibilities. I could do the maximum number of positive, minimum number of negative, but that would only be 2, so I'd need 4 imaginary. Or I could do the minimum number of positive, maximum number of negative. Again, that adds to 2, so I'd have to have 4 imaginary. This example came out very similar to the last one, so I only have 4 possibilities. I don't need that final row of the table. Please know that the number of positive and negative will not always match, just coincidental for these 2 examples. I didn't list out P and Q yet, so let me go ahead and do that. So P is 1, so it's plus or minus 1. Q is 2, so it's plus or minus 1, plus or minus 2, which means your possible zeros would be P divided by Q. So 1 divided by 1 would be 1, 1 divided by 2 would be 1/2. So there's 4 possibilities. I know based upon Descartes' rule of signs that at most I could have all 4 of them work out, the 2 positives and 2 negatives. Let's take a look at the graph to figure out which of the 4 rows in our table it actually is. Okay, so when we graph this function, we can see there's 2 positive x-intercepts. Two x-intercepts to the right of the y-axis, and there's none to the left of the y-axis. There aren't any in the negatives, which means this row is correct. There's 2 positive, 0 negative, and 4 imaginary. So that means, we would toss out all of the negative possible zeros. We know they're not correct. We can use the 2 positives to get it down to something that we could then solve to find the imaginary. So that's Descartes' rule of signs. It's just another way to, first of all, check your answer and make sure you're right. Narrow down the possibilities as you're trying to find your answers. And just shed some more light upon polynomial functions.